Welcome to NASA Edge.
An inside and outside look at all things NASA.
We're here at the NASA Jet Propulsion Laboratory in Pasadena, California to talk about the Low-Density Supersonic Decelerator,
also known as LDSD,
which is part of the Entry, Descent, and Landing portfolio.
Over the course of the show, we're going to be talking to a number of engineers and researchers, and they're going to provide us a status update on the project.
And we'll learn about the future of this technology demonstration mission.
So like LDSD, slow down, relax, and enjoy the show.
Hey, and watch out for the deer too.
Yeah, they run the place out here.
So Ian, it's great having you on the show again.
Thanks for having me.
And I guess you're just recovering from an open house here at JPL?
Yeah, Saturday and Sunday, we had 45,000 people come through JPL to hear about all the things going on here. And it was really nice because we got to share some of the enthusiasm, show them some videos from LDSD, talk to them about the future and all the cool things that we're going to do.
Yeah, and plus all this noise going on, they're cleaning up from that event. So I mean, you had all these tents, chairs. I mean, it's pretty big.
Yeah, it's definitely a pretty big production, and it's going to take a couple days to clean up.
Yeah.
So.
Now, the last time we had a chance to talk with you, you were talking about an upcoming test at China Lake.
Yep.
In fact, you probably had a number of tests since then.
Yeah.
But before we actually get into the results of those tests, kind of take us through what low-density supersonic decelerator is all about.
So, a couple years ago, we put the Curiosity rover on the surface of Mars. This was a 1-ton nuclear-powered, laser-equipped rover. It was the largest, most massive thing we've ever landed on another planet. The capability to put that on the surface of Mars was basically using technologies that we've had for decades, going back to the Viking program in the early and mid-1970s. As we look to the future and we want to do more exciting, more capable, more bold science missions, and as we cast our eyes to the horizon and we start thinking about putting humans on the surface of Mars, we're going to need new technologies that allow us to take those very, very large, very massive payloads and slow them down adequately enough to put them safely on the surface of Mars. That's what LDSD is about. We're developing the next generation of decelerators that will allow us to land these very large, very massive payloads that you're going to need as we look into the future.
And that's one of the challenges is entry, descent, and landing for any planetary surface, but especially Mars.
For anybody with an atmosphere, absolutely, is the entry, descent, and landing. And Mars is particularly challenging in the solar system because the atmosphere is so thin. You know, Earth, we've got a very nice, thick atmosphere, and it's relatively cushioned to decelerate in. There's a lot of air, a lot of things to react against the surface. At Mars, the atmosphere is extremely thin. It's about 1% the thickness of Earth's atmosphere, which means that you don't have a lot of atmosphere to react against the body, which means you need really big bodies to react against what atmosphere you have.
So looking at the LDSD project, to kind of take us through the different aspects of LDSD.
Well, it starts with the technologies. We're developing 2 new flavors of supersonic decelerators. Devices we call supersonic inflatable aerodynamic decelerators, or SIADs, and extremely large parachutes that can be used at Mach numbers at speeds much higher than we've been able to use them in the past. From there, it goes into the idea that before we use these technologies at Mars, we need to make sure that they work the way that they need to, that we understand how they work, and that we get the performance that we need from them. That means we have to test them, and that's actually one of the hardest aspects of this entire project, is that the size of the devices that we're developing and the conditions in which we're going to be using them are things beyond whatever test capabilities we've had since really the dawn of the space age. For 50 years, you know, we've outgrown all of the tools, infrastructure, and capabilities that we've got for doing testing on these size devices. So we had to come up with new techniques. That means things like rocket sleds out in the desert, or high altitude supersonic flight tests like what we conducted last year and what we'll be conducting again next year.
So let's go back. We interviewed you here at JPL about a year and a half ago,
Yeah.
and you had an upcoming sled test. Kind of take us through that test, and what were the results?
Well, we were out in the desert, we were at China Lake, and we were doing some testing on SIAD-R. We wanted to take SIAD-R up to loading conditions, aerodynamic loading, similar to what we would see if we were to use it at Mars. So what we did is we built a 20-foot tall, 40-ton welded steel siege tower with a Mach aeroshell on the front of it. We took some surplus solid rocket motors, we lit those, and we got from 0 to 300 miles an hour in a few seconds.
Wow.
Once we got up to those speeds, we deployed the SIAD. We saw it inflate in a fraction of a second. We saw how it emerged from a very tightly compact, stowed state into a fully deployed, fully inflated state. We got a feel for how much inflation pressure was necessary to see this thing act as a rigid structure. We got to load it aerodynamically, put all the pressure and forces that are going to be on it if it were used at Mars. And we got to see how it did under all of those conditions. It did flawlessly. You know, it was inflated beautifully, it held the inflation, it held the shape much longer, much better than we thought it would, and it survived all of the loads just great. You know, it's kind of interesting for those kinds of tests. I say we were going 300 miles an hour. We were only going 300 miles an hour,
right,
because when we use these devices at Mars, we're going to be going several times faster than that.
Okay.
But to replicate the loading, the aerodynamic loading, because the density is so much higher here in the surface of Earth than it is at Mars, you don't have to go as fast to get that same loading.
That's true, that makes sense. So was that a full scale?
It was full scale,
Okay.
yep. The full scale air shell, 4.7 meters, and then a 6-meter diameter side R.
So now you kind of worked to the next level. You want to do an altitude test where you're dropping it vertically?
Yep, so that was really aerodynamic loading. We got to see some initial deployment kind of data. We really want to see how these things fly.
Right.
Do they deploy in a free body sense? In other words, once this thing's flying through the sky and it begins inflating, what's the motions of the device like? Does it inflate on one side more than the other and begin to tumble the aeroshell? You know, what are the aerodynamics in a supersonic environment? So to get all that kind of information, you have to take a full-scale device to conditions that are analogous to what it would see at Mars. That means going several times faster than the speed of sound, and it means doing it in a very, very thin atmosphere. Well, there is such a place here on Earth, you just have to go halfway to the edge of space to find it.
Okay.
And halfway to the edge of space is about 50 kilometers, or almost 180,000 feet. So what we did is we built a test vehicle that looks very similar to the entry vehicle that lands Curiosity on Mars. We took it up to an altitude of 120,000 feet using a balloon the size of the Rose Bowl. The test vehicle itself weighs 7,000 pounds. Once we got up to that altitude, we released from the balloon and we lit a giant solid rocket motor. That rocket motor took our test vehicle from an altitude of 120,000 feet to an altitude of 180,000 feet and got us going to over 4 times the speed of sound. Once we got to those conditions, the motor burned out and we began our test. We got to inflate the Syad. We saw that inflate in a fraction of a second at over 4 times the speed of sound, nearly 3,000 miles an hour. We watched it decelerate the vehicle. We deployed another device, a balloon parachute at nearly 3 times the speed of sound, over 2,000 miles an hour. We saw this device work flawlessly, and we used that device to help pull the parachute off the back of the test vehicle and get it out behind the test vehicle at about 2.5 times the speed of sound. We then tried to take 100 pounds of nylon and Kevlar and get it to inflate properly in a 2,000 mile an hour wind.
Wow.
What we saw is that it didn't inflate the way that we wanted it to. It got damaged in the process. But now we get to use that data that we didn't think we'd actually get this year, data that we thought we'd have to wait till next year. But because we had all of these technologies ready a year ahead of schedule, we get this data early. We get to take this data, learn from it, and now we're applying that knowledge to building stronger, better parachutes that we'll be testing next year.
Yeah, that was some great information that Ian Clark gave us on how the LDSD project is developing.
And I had a chance to sit down with John Gallen, who works on the parachutes for LDSD. And he talked about the recent test in Hawaii and the challenges they faced. But he also talked about some of the challenges they faced during recovery of the test vehicle. So John, earlier Ian mentioned that the test was a success. So were you able to see this real time, or were you, where were you during the test? How about that? That would be a good place to start.
So during this test, I was actually out on the recovery boat. So we were out in the Barking Sands Pacific Missile Range in the water that they control to the west of Kauai. We were just outside of where the predicted landing ellipse would be for where the test vehicle could actually splash down at. So from that point, we actually had a beautiful view of the test article. It was very small in the sky, but we were able to actually see the balloon as it got to its float altitude. And then through the radio system, we were able to actually hear the countdown and watch, and we could just see the contrail of the rocket shoot across the sky.
Were you able to recover everything, or did you only get the test vehicle or the black box, if you will?
Yeah, we were actually able to recover everything that we set out to recover and even more. And we actually came up among some other stuff that we were able to recover that we didn't even think we were going to see, namely this balloon system that actually was used to deploy the parachute. On the way to get to the test vehicle, we actually found it floating in the ocean. So we were able to real-time make some decisions on if we wanted to attempt to recover it, even though it wasn't in our list of top priority recovery items. So we all kind of put our heads together and said, yeah, we're going to try to recover this balloon. But we put our time limit on it of 15 minutes. We can't get it out of the water within 15 minutes. We're just going to leave it and go straight to the main objective. There was also, this isn't something we had even talked about recovering, and the fact that it actually could have a live pyrotechnics still on board. I needed to brief, the EOD, the Explosive Ordnance Team, to, how are you going to recover this? What do you need to look out for? So in real time, I gave them a complete briefing, told them of the hazards, how much ordnance was on board, where they would look to see if it had fired or not. And this all happened in the course of about 15 minutes by the time, we said, hey, we're going to recover the balloon, and at the point that we actually got the boat to the balloon.
And I would have just said, this isn't on our list, too bad. But it seems like you scored a huge victory in being able to recover some pretty important data.
It was, because we needed to know, how well that balloon worked. If we would have thought we'd ever recovered it, would it got put on the list? It definitely would have.
So you got the balloon, and that's great, but how did it go once you actually got to the test vehicle?
Yeah, so once we got to the test vehicle, we basically had two boats. One was what we call the fast boat. It actually was able to get to the test vehicle before the big crane boat that we actually would use to pick the test article out of the water. So the first boat got there. It had two Navy EOD divers on board, as well as two of the JPL employees, to basically evaluate the situation. So they couldn't, pull the vehicle out of the water, but at least they could get there. The Navy guys had some buoys. They had, all of their dive gear and stuff that they would be able to go in, get on the vehicle, and start to pull off the critical data, like this little black box item, which had all the critical data in it. And then it went on to securing the test vehicle. We wanted to make sure that we could recover as many of the test assets off of the vehicle. Fortunately, once we got there, the parachute had totally sunk, and it was actually straight underneath the test vehicle, and it was actually kind of pulling at the test vehicle a little bit. So basically, they cut the parachute free. They were able to transfer that structural load over to the boat, and the boat was actually able to move away from the test vehicle, basically holding the parachute, keeping it from sinking, as well as making sure that the test vehicle remained afloat and wasn't getting yanked underwater by this parachute. And then shortly thereafter, the EOD guys actually stayed and sat on the test article until the large boat, crane boat, was able to come over. And at that point, we started the recovery efforts of getting the test vehicle out of the water. So when the day was done, we recovered all of the items that we set out to do, and plus the balloon.
Franklin, it seems like John had a great time being on the recovery team on the flight test out in Hawaii.
Yes, and he was also out there with Rob Manning, who was the chief engineer for LDSD. And we sat down and talked about the design challenges that he had to address through testing. So Rob, you're the chief engineer for LDSD.
Yes.
You've worked with Mars missions prior to what maybe LDSD might be used for down the road. You've had missions that have gone to Mars where you didn't test these parachutes like that.
That's correct.
So what's different between then, say for instance, what you did with Curiosity, Pathfinder, and even Viking, to moving forward to LDSD where you are now? What's the difference?
Well, I think the biggest difference is those parachutes were all designed to conform to architecture and design principles that were tested at high altitude in the 1960s and early 1970s. So there was 3 test programs where high altitude balloon would lift up a parachute with a simulant of an entry vehicle and launch it way up into the upper atmosphere, just like we're doing above New Mexico, and test out these parachutes to see how well they work, especially how well they inflated in those conditions. We've been counting in those test results for 40 years, and that test program has given us confidence that the parachutes we design will inflate. Now, we still have to make sure that the parachutes were designed to be strong enough, so what we can do is inflate them in Earth conditions in giant wind tunnels and get the strength tested that way. But we can't reproduce the high-speed inflation part. We're counting on those test results from the past. So when my team and I said, let's build a rover like Curiosity. Well, what's the biggest parachute that was ever tested in the 1960s and 1970s? There was one parachute that was tested that was just about the size of Curiosity's. And then we said, okay, we're using that test result. We analyzed the video, looked at the test results, watched how it opened, watched how it bounced.
Hold up, but it's also based on the weight of your
vehicle?
payload, of the vehicle, right?
It turns out, because the inflation process is so fast, the weight of the thing that's pulling on it isn't playing a very big role.
Really?
The weight doesn't play a big role. Instead, the size of the vehicle plays a role, because what that does is it produces a wake, a supersonic wake that flows back to the parachute. So what we really need is not so much something that's that heavy, but something that doesn't slow down too fast during the inflation process. Because the inflation process is so fast on Mars, it doesn't have to be exactly the same weight. And back then, the weight wasn't that high, but the size of the forebody, the heat shield, the wake was about right. So again, so we could take advantage of that. Now on Earth, weight does play a role because it takes such a long time for the parachute to open. So by the time the parachute is open, you've already slowed down to half your speed. On Mars, boom, it goes from nothing to something in a matter of half of a second.
Okay, so in LDSD, you have your supersonic parachute, but that's only half of what you're working with. You have the SIAD that deploys.
That's right. So we did a twofer. We did 2 tests in one chance last June. What's so nice about a SIAD, it doesn't weigh a lot, and it's pretty easy to pack around the aft body of the space capsule. So we can pack it there, and with a pretty small gas generator, we can inflate it, boom, and add to the diameter of the heat shield.
Right.
The cool thing about that is that now we can get a bigger vehicle that would otherwise have to inflate its parachute at 3 times the speed of sound. Instead, we can use it to slow down from, say, Mach 4 down to Mach 2 without losing too much altitude. I mean, the problem here is that you're running out of space. But if you wait too long with your parachute, you hit the ground. So in our case with LDSD, we said, well, if we could try out this SIAD technology, we could even go to bigger systems, bigger than Curiosity. And if you add to this, a new supersonic parachutes, even that's twice the area of Curiosity's parachute, then we will really have pushed the envelope and allowed future designers, future mission designers, to land things that right now I can't land, because the largest parachute ever tested successfully was back in 1972.
What's the difference between the speed of, say, for instance, when Curiosity entered Mars' atmosphere versus what you'll send to Mars 10, 20 years from now after the SIAD has been deployed?
In all cases, we don't think we could test, we don't want to test parachutes much above Mach 2. The reason is that if you go to, say, Mach 3, the temperature, the friction of the atmosphere at those speeds will melt the fabric. So in all cases, we're trying to get the whole vehicle down to a velocity and altitude where the parachute will work, and that's around Mach 2 to Mach 2.5.
And that's what you've managed in the past.
And what's managed in the past, and what a SIAD does, it allows you to have bigger vehicles to take you into that realm without getting too close to the ground.
It's almost like downshifting your car.
It is. It's like exactly. It's like a transmission. You got to get in the next velocity regime, an altitude regime, so to use your equipment safely. And so really, that's why a SIAD and this parachute really do go together for bigger vehicles.
Looking at the data you've received from the Hawaii test and your helicopter tests, what are your design challenges going forward to develop the supersonic parachute?
Okay, well, the first design challenge is first to figure out what were the actual stresses on the fabric during inflation. Is it possible that we underestimate how much force is applied to these parachutes under supersonic conditions? Or was there something about that parachute that made it weaker than we expected? That's a number one primary question. The other question is, what happened in this test where it actually failed well below our expectations? It could tell us that maybe it's not something about supersonic, because we've never had this kind of failure. If you look back at all the previous supersonic flights in the 1960s and 70s, they never had this kind of failure. So we're thinking that maybe there was something about how the manufacturing tolerances stack up when you make something this large that might be a potential cause, but there may be other causes. So our biggest challenge is, okay, now how strong do I make the next parachute? I could make the parachute a lot stronger. We could put much more Kevlar on it. We can just go to town making it stronger and heavier and harder to use, because if I make the parachute too massive, then nobody's going to want to use it, because it's just not paying for itself anymore.
Right.
So the right thing is to find the right balance between making it strong but not too heavy. And that's the real challenge. Can we come up with computer simulations and models that make accurate predictions of the stresses in that fabric and structure during supersonic inflation? And that's what we're doing now. And if we can do that, we will win this game.
Okay, Ian, what's next for LDSD?
We're still going. We got more testing.
Okay.
We had the parachute data that we got from this year's test. We're taking that knowledge, we're applying it to how to build better, stronger parachutes. And we've got 2 more high-altitude supersonic flight tests in 2015.
That'd be in Hawaii too?
And those will be off the coast of Kauai, absolutely. We have more sled tests. Once we have this new parachute design, we're going to go back out to the desert and we're going to expose it to over 100,000 pounds of force and make sure that parachute's strong enough to survive the forces it's going to need to survive, again, if it's going to be used at Mars. We've got more sled testing on the SIAD device, the device that we're targeting for things 3 or more times the size of the Curiosity rover. And it's the data from these tests, in particular the data from the high altitude flight test this year, and those technologies that are really going to be driving the future of the missions that we do to Mars, and hopefully one day be used to land humans on the surface of Mars.
And I assume that at some point in the future, you'll actually have a high altitude test with the SIAD E? As well?
That's our hope.
That's
Right
our hope,
now
right?
for 2015, the 2 tests are targeted with SIAD R
Okay.
and parachute, and trying to get the parachute fully inflated at the test conditions that we need to, and maybe even trying to deploy the parachute in a new way, constrain the opening diameter, reef it, it's called, to not generate as large as the loads and maybe have a more controlled opening. That's one of the things we're testing.
How soon could you even think of having a mission, let's say a robotic mission using SIAD, the
Oh,
SIAD
yeah.
concept, or the LDSD concept going to Mars?
Well, in theory, by the end of this project, these technologies, particularly the SIAD and the parachute in particular, will be ready for adoption in a flight project. That means that at the end of next year, we will have all the data and we will have conducted most of the testing necessary for them to be incorporated onto a flight project. You just sort of look on the horizon and see, well, what opportunities do we have for missions to Mars? We have a couple coming up in the near term. The 2020 opportunity that's very similar to the Mars Curiosity rover. It's more likely that the missions coming behind that one after 2020 are going to be using these technologies. For example, the 2020 mission has a caching component associated with it. It wants to collect a number of samples that we hope to be able to retrieve and bring back to Earth. Well, the mission that comes after that is going to have to go retrieve that sample, load it onto a rocket that takes it from the surface of Mars at least up into Mars orbit. That's an enormous system, and that's a system that's going to require, at minimum, a larger, better parachute like what we're developing, but possibly a SIAD as well.
That's just awesome, Ian. And just think, maybe your concept will be used
Yeah.
when we land the first humans on Mars.
Well, that'll be exciting. I want to keep going. So
Right.
I want to go bigger. I want to develop more technologies. You know, the technologies we're developing,
Right.
we're targeting things bigger than Curiosity. But I've told you, on the horizon is one day putting humans on the surface
Right,
of Mars.
right.
So, I'd like to be able to keep going with these kinds of technologies and develop them further to make sure that we have that set enabled for when we want to go land humans on the surface of Mars.
Well, I think Ian Clark will be a name to remember when the first humans to land on Mars.
Well, hopefully LDSD, because it's an enormous team. Again, a very amazing team that we've assembled here at JPL and across NASA and across all of our industry partners. The Navy, the Columbia Scientific Balloon Facility, our NASA centers, Langley, Ames, Goddard, Wallops, all across the nation. It's just a really phenomenal team that we've got.
Ian, thanks for joining us again. Appreciate the update on LDSD, and we look forward to seeing more great things about the project in the next couple of years.
Thanks for having me.
Ian, John, and Rob gave us a great overview of the LDSD technology demonstration mission.
Entry, descent, and landing is one of the critical challenges we're going to have to overcome if we're going to land humans on Mars.
And the challenges don't stop with LDSD. We're going to look at several EDL projects on future episodes of NASA Edge, like Thor, for example.
Right, dropping a hammer early.
You're watching NASA Edge.
An inside and outside look
At all things NASA.